In the previous unit, you learned how a gas's properties change when a high-speed flow is brought to rest or stagnated. You also examined the opposite situation, where a gas from a high-pressure reservoir was allowed to freely expand. But what if you want to control how such a flow behaves? For example, to maximize the amount of thrust that can be generated by the exhaust from a scramjet. This can be achieved by using a nozzle, which is essentially just a flow with area change. In the next few units, we'll examine ideal nozzle flows. Our main goal will be to develop the theory and understanding necessary to analyze the flow through an idealized scramjet nozzle. The purpose of this nozzle is to convert the abundant thermal energy of the high temperature gas exiting the combustor into kinetic energy, so that the high-speed exhaust will impart maximum thrust to the vehicle. The natural question to ask is, if this nozzle is supposed to accelerate the flow, why is its area increasing? In our everyday experiences, if we want to accelerate a fluid, we usually reduce the area it flows through. For example, if you're using a garden hose and you want to generate a high-speed jet of water to wash away some dirt, for example, you can do this by putting your thumb over the end of the hose. The same effect can be achieved more precisely using a nozzle such as this one, where we can see that the area is tapering in towards the exit. An extreme example of generating a high-speed flow with a converging nozzle is this water jet, which is being used here to slice an apple, but could also be used to cut rock or metal. On the other hand, if we examine the Space Shuttle main engine nozzles, which are also required to accelerate an exhaust, we can clearly see that the end of the nozzle area is diverging. So why do these nozzles, which are all supposed to accelerate a flow through them, have what seem like contradictory designs? The answer is compressibility effects can completely change the way a flow responds to an area change. In the next unit, we'll go through the theory required to understand this phenomenon.